Okay, good morning and welcome back. Today we will talk about special theory of relativity. Before we start, I would like to go back to the first page and we will make a brief review of what we have learned so far. Go back to page 1. We will talk about special theory of relativity. Remember, we make two postulates. One is law of physics are invariant in form in all Lorentz frame. The other is the speed of light in vacuum has the same value c in all Lorentz frames. Lorentz frame means the inertial frame. Okay, actually, uh, the speed of light in vacuum has the same value c in our Lorentz frame, give us the Lorentz transformation. And then today we will use the Lorentz transformation to show you why laws of physics are invariant in form in all inertial frame or Lorentz frame. So remember here we mentioned in Appendix A, we will tell you how to find the Lorentz transformation. It's a college physics for freshmen, so you can study by yourself. I just upload Appendix A to the ILMS system, so you can study by yourself. Okay, remember we have a different viewpoints. For these two postulates, different textbook has different description. For example, Griffiths, he said the principle of relativity. All physical law has the same form in all inertial frames. And second postulate, he said the universal speed of light. Okay? And what is Lorentz transformation? Actually, it's here, denoted as this symbol. We have a relation between gamma and minus gamma beta, minus gamma beta, gamma. Because we have four coordinates, x0, x1, x2, x3, and beta is the relative motion, v over c. Beta is a normalized quantity, and gamma is defined here, okay? But gamma, remember, they move along the x-axis, along the x-axis. That's why the major change is in s-axis and time and x. That's the Lorentz transformation matrix. Okay, and we talk about two vectors. One is control variant with superscript. The other is covariant with subscript. Superscript, subscript. Okay, up and down. And we will use Einstein notation, summation convention. Einstein simplified the notation. If we have beta, one superscript, one subscript, that means they will sum 0, 1, 2, 3. Okay? So simplify uh, the summation notation, the summation convention. Okay. Here, how to what is the difference between superscript, covariant, control variant, and covariant? We can just use a metric form. So by doing so, by using the metric tensor, we can rise and lower the index. For example, if you want to rise For example, if you want to lower the index, in this case, subscript, we just times G alpha beta and sum over beta. If you want to rise, okay, once again, G alpha beta and sum over beta. So if we write express in these components with the metric tensor or a covariant vector and a contravariant vector and a covariant vector can be expressed as this one and this one. For 0 par, 0, the same, but for position, they differ by a minus sign. Okay, in terms of vector form. Okay, and give you two examples. Now, today we will start from page 12, and we will cover more page than we used to. We will cover from page 12 to page 26. We will talk about how, what is the operation rules. So therefore, I will show you how to use Lorentz transformation matrix. We will define and we will show you the we will show you all physics law have the same form in all Lorentz frame through Lorentz transformation. Okay, we will show you what is a four vector and four momentum and the inner product, uh, Lorentz invariant, and four tensor of the first rank, four tensor of the second rank, and four tensor of the third rank. The mathematics we learn here will be used in section 2 and section 3. Okay, so if you don't if you have no feeling at this moment, you can study later. Just use the real case and you can compare. You can have a better understanding later. So first, let's define a position vector in four-dimensional space of x and t. That's a position vector in four-dimensional space time x, y, z. In short, CTX. Mu runs from 0 to 3. That's the row number. In a 4D matrix as this one. And mu runs from 0 to 3 as a column number. Column numbers. Row number. 0, 1, 2, 3. Column number 0, 1, 2, 3. And beta is V divided by C. Okay. Gamma equals 1 minus beta square. Take the square root 1 over square root 1 minus beta square. This one is always less than 1. Okay, the minimum value is 0. Okay, therefore gamma will be always greater or equals 1. And beta, the maximum value will be 1. Okay, just give you an idea. And we have no change, no relative motion in y and z. Therefore, in the y and z, no change at all. Some people simplify this notation to two dimension, one x, t and x, but it's not convenient. Therefore, we still keep 4, including 2 unchanged components. So the Lorentz transformation in 1 can be written in this one. So we have two coordinates, coordinate k prime system with a variable ct prime, x prime, y prime, z prime, and the other is the k frame unprime system. The relation between prime system and unprime system is simple, just Lorentz transformation. Or you can write into this form, or you can use Einstein summation convention. Simplify the notation a lot. Okay, lambda, mu, nu. Okay, that's the Lorentz transformation. No, people denoted as lambda, capital lambda. Okay, now we will talk about inner or scalar product. It's defined as the product of components of a covariant and a contravariant vectors. B dot A, just like B mu A mu, okay? B mu A mu. So if we have another one, that's a two vector inner product in unprime system. If we express two vector in prime system, B prime dot A prime, we got this one. Remember, we have Einstein summation notations. After the summation, sum over beta, we got x prime alpha. And in this case, after the summation, sum over lambda, we got a primed alpha. So we have b primed alpha and a primed alpha. Okay, that's why we can express in this form. But this is related to velocity only. It's a constant. So you can move this one and this one together. You can move to here, and partial x prime alpha, partial x prime alpha, the same, cancel. So eventually you got partial x beta, partial x lambda, like this one. Just imagine this is ct xyz, and t, s, y, z are independent variable. So only when beta equals lambda, we got value. Otherwise, nothing. Okay, so eventually we have delta, beta, lambda. We can express in this form. We use this property. We use this property substitute to here. So sum over beta, we got only when beta equal lambda, we will have non-zero. Otherwise, this is 0. If beta is not equal to lambda, 0. So, interestingly, we find the inner product do not change. The inner product of two vector, covariant and a contravariant vector, do not change. Just as the three-dimensional vector and tensors in general are defined in by their transformation properties in the X space, we may define the four vectors and the four tensors in general by their transformation property in the X and T space and found rules for their operations. So we are going to find the rules for everything. For, for example, the first one, I will show you we have four positions. We have four positions. This one, the position vectors, we call four positions. So first, any set of four quantities, any set of four quantity, 0, 1, 2, 3, which transform in the same way. These three quantity transform in the same way as x mu. That is a just like position four vectors transform exactly the same way as Lorentz transformation. We call it a four vector. A four vector is a four tensor of the first rank. That's a four vector. So any four quantity, any set of four quantities satisfy the Lorentz transformation, transform in the same way as this one, then as a four vector. Okay. The position vectors of a point in a four-dimensional space is obviously a four vector. We just shown you. Another example is the momentum vector of a particle. But momentum, we have three components, ps, py, pz. How about the first component? Okay. In order to obtain the first component, we introduce E over C. So now we have four components. How do you know the first term is E over C? Why not E over 2C? How do you know? We should have the same dimension. So E over C is the same dimension as momentum. So E over C dimension is correct. But why not 2C? If we use 2C, it's the same, right? It should be the same. But why we use E over C only? Okay, because E over C is simple, and later on we will show you E over C is more accurate because they will demonstrate some important properties. So you can write maybe 2C, 3C the same, just like 2P, 2P, 2P. Transformation should be the same. But later on, I will show you they have some properties from the mechanics. Okay. So now it's a four vectors because they transform in the same way, as four position. So that's four momentum vector. Okay. Anything else? We will find more and more set of four quantities later on. Okay. What else? I will show you second, if a quantity phi is unchanged under Lorentz transformation. If this one is unchanged under different inertial frame, then it is called a Lorentz scalar. A Lorentz scalar. That's four vector of the zeroth order, zeroth rank. Four vector of the zeroth rank. The Lorentz scalar is also called a Lorentz invariant, Lorentz scalar. The Lorentz scalar is in general a function of the components of a four vector. For example, we have just shown that the s prime equals the x prime mu, the x prime subscript, superscript, contravariant, covariant. And this one can be read into Lorentz transformation. Sum over beta, so we got this one. Sum over mu, or lambda, so we got this one. Superscript. And this one can be rewrite into this one, cancel. So eventually we have delta function, but this one is connect delta. That is beta equals lambda, then this one is 1, otherwise 0. So we can rewrite into the s square. So the s prime square equals the s square. That is independent of inertial frame. The value is always the same. So the s square is a Lorentz invariant or Lorentz scalar, independent of Lorentz transformation. Good. Second. Third, let's define a four-dimensional operator. Remember, in the three dimension, we have gradient, we have curl, we have divergence. How about in the four dimension? We can define the same notation, similar notations, as the counterpart of the operator, this one, del, in X space. So we define partial alpha, just like partial X alpha. Remember, this is a lower index subscript. So we can denote as this form. And this is the major difference is here. But remember, here is different from alpha by a minus sign. Therefore, in terms of four-dimensional operator, we will have a minus sign here. You might expect the minus sign should be, this should be a positive sign for superscript, for contravariant. However, remember, this is an operator. Operator is ready to operate on something. And this is in a denominator, not the numerator. That's why we have a minus sign here. So on the other hand, four-dimensional operator, we can write into this form. So that's the major difference. Minus sign here and plus here. Okay, that's the major difference. And gradient phi, we can is defined as this form. Okay, gradient phi. So this one is very similar to three-dimensional, but we have one extra terms. Then the four gradient of a Lorentz scalar. Four gradient, gradient 2, 3, 4 of a Lorentz scalar is a vector. This is a vector. How to prove that? A vector, four gradient of a Lorentz scalar is a vector. That's a little bit surprise. But remember, if it is a four vector, then their transform should be in the same form as Lorentz transformation. So we just show you partial mu prime phi is a Lorentz scalar, and this one is prime system. If we can show you this is transform in the same way as Lorentz transformation, then it is a four vector. Okay, so how to do that? Partial phi, just write it down. Partial x prime mu, and prime system is transformed in this way. Partial x mu, partial x prime mu, nu mu. Okay? So this one can be write into Lorentz transformation. Nu, nu, nu. Okay? Transform as a four vector. Okay? Therefore, we prove the four gradient of a Lorentz scalar is a four vector. We have more properties to go. The four divergence of a four vector. Now we can generate a four vector from the divergence of a Lorentz scalar, Lorentz invariant. Okay, so can we divergence a four vector? Yes, we can do that. How to do that? Denoted as just like three-dimensional. Three-dimensional, we have divergence A, and we have four divergence A, but A is a four vector, not just a three components, it's a four components. So we can define it as partial A mu, partial S mu is a Lorentz scalar. Once again, if this one is a Lorentz scalar or Lorentz invariant, it will be independent of Lorentz frame. So proof, the step one is define the notation as this one, just like del, three-dimension del. So partial mu can be read into this one. That's Griffith's notation. However, unfortunately, Jackson symbol is incorrect. In 11.78, he defined this del, four-dimensional del, as this one. So it's incorrect. Correct form is square. Okay, Griffith is correct. We will correct Jackson's typo later in next page. Okay, so if we want to show you this one is a scalar, then we will show you this is independent of Lorentz frame. How to do that? Just write it down first. Prime prime. And remember, each component is four vector. We can transform as Lorentz transformation. So first one, this one correspond to this one, and this one and this one correspond to this one. So these two, once again, cancel. Eventually, we got a connected delta, mu lambda, mu lambda. Okay, mu lambda. As we sum over lambda, we got only when lambda equals mu, we got value. So this one is divergence A. Therefore, divergence A is unchanged under Lorentz transformation. Okay, therefore, they are Lorentz scalar or Lorentz invariant. Note, we always change a component from prime to unprime or from unprime to prime. Use these notations. Okay, let's property number 4. Property number 5. Okay, I just promised you to correct Jackson's typo. Jackson actually should be defined it as this one, not without 2. Property number 5. The 4 Laplacian operator is denoted as partial alpha superscript subscript. And in terms of this one here, and if we write it down, it's just like, yes, we recognize this looks like this way will generate wave equations. Okay, so that makes sense. Makes sense to us. Makes sense why we use CT, not 2CT or 3CT. That makes sense. Let's Lorentz scalar operator. This one can operate on Lorentz scalar, and the result will be the same. Because this one, how to prove that? We have shown in terms of 4, in item 4, that the divergence of a 4 vector is the Lorentz scalar. So we can use the same properties. Divergence of a 4 vector is a Lorentz scalar, all denoted as this form. Divergence of a 4 vector is a Lorentz scalar. Let phi be a Lorentz scalar. Then we can express a vector as a divergence of a Lorentz scalar. Okay? This vector is derived from Lorentz scalar, and this one is also derived from Lorentz scalar. They are 4 vector. And once again, divergence of a 4 vector. So we can write into this form. Just substitute everything to here. And we can write it down after the Lorentz transformation. Move this one to here. We have a connected delta lambda over beta. Same argument always. So eventually we got these 2 terms. This one gives us here. This one gives us A beta. And only when lambda equals beta, we have value. So this one can be simplified into divergence of a 4 vector. Okay. In other words, we just substitute A using this property again. We have Laplacian, 4-dimensional Laplacian. That's 4 Laplacian. 4 Laplacian prime on a Lorentz scalar equals 4 Laplacian on a Lorentz scalar. Invariant, doesn't change at all. That's item number 5. Move on to item number 6. Now we still has 6, 7, 8, 9, 10, 11. Yeah, we still has 6 to go. Take a break. Any questions so far? Take a break and drink some tea. We will be back in 30 minutes. Item number 6. We will talk about the inner product or the scalar product or the dot product of a 2 4 vectors is Lorentz scalar. Actually, we talk about this idea at the very beginning. Now, I will show you in more detail. Let's a dot product of a four vectors. This is a Lorentz scalar. Lorentz scalar means independent of inertial frame, Lorentz frame. First, let's recall A prime system. We can write into this one. And partial x prime alpha, partial x beta. And the same, likewise, B vector B prime, similar notation. So the inner product of two four vectors, prime prime, A prime sigma, B prime sigma. Maybe we should use alpha. Alpha. It doesn't matter. uh, Alpha, sigma, sigma, the same, just notation. So this one substitute to here, and this one substitute to here. And once again, we have two terms, this one and this one. This one and this one. And cancel. Therefore, only when, cancel. Only when mu equals lambda. So it's connected delta again. Only when mu equals lambda, we got a value. So we have A lambda times B lambda. Okay. At the beginning is prime system, but now is unprime. So it's A prime dot B prime becomes A dot B unprime. Okay? And we have other expressions. For example, this one the same. And you can lower the index using the metric or the norm tensor. You can lower the index, raise the index, okay, using the norm tensor. And once again, this gives us connected delta. So sum over sigma give us delta alpha beta. Therefore, sigma sigma. So A sigma prime B prime sigma equals to this one. Okay, the same notation, a different notation, but the same physical meanings. Therefore, some people say uh, that looks like a row vector times a column vector. However, if we consider this one as a row vector and consider this one as a column vector, so a row vector times a column vector is a scalar. However, this one is a column vector times a row vector. It's not scalar. You will be confused. Therefore, I don't want to overemphasize the vector operations. We will use index. Later on, we will encounter the similar problems. I just want to show you. You might be confused. However, this one can be changed to this one. No difference. No difference. Okay. We just show you. No difference. No difference. Okay. They should be the same. Therefore, if you think the vector tensor operation from the idea of column vector, row vector, you will be confused sometimes. I prefer to stick to use index. A tensor, so we have the tensor of the first rank, tensor uh, 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 for for gradient, for we are going to define a tensor of the second rank. we use a notation F. It's a second rank. So a first rank, we have 4 components. Second rank, we have 4 by 4. So we have 16 quantities. How to do that? F prime alpha beta. Okay, and alpha beta runs from 0 to 3 and transform according to this one. Each components, we have gamma. Gamma will transform in this way. Delta will transform in this way. Okay, and this one will give us Lorentz transformation alpha gamma. This one gives us another Lorentz transformation beta delta. So we have 4. We have 2 Lorentz transformation, not just one. That means if we want to transform a 4 vectors, we need just one Lorentz transformation. If we want to transform a 4 tensor of the second rank, we need 2 Lorentz transformation. It implies if we want to transform the 4 tensor of the third rank, we need 3. Okay? Contraction with a metric tensor or a norm tensor, G alpha beta, G alpha beta, superscript subscript, is the procedure of changing an index on a tensor from being contravariant to covariant. Oh, there is a typo here. Contravariant, V-A-R-I-N-T, a typo, and vice versa. So if we want to change from contravariant from covariant to contravariant, we need to contract with G alpha beta. On the other hand, if we want to lower the index, we need 2 times G alpha beta. The covariant 4 vector X alpha can be obtained from the contravariant. That is, covariant and contravariant can be obtained from metric tensor. Okay, you can rise and you can lower. You can lower here. You can rise here. Okay, that's item number 7. Item number 8. A dot product of a 4 tensor of the second rank and a 4 tensor. Okay, that's not an inner product. That's a 4 tensor of the second rank, inner product with a 4 vector. So 4 by 4 times 4, 4 by 1. You can, not the best idea, 4 by 4 times 4 by 1. So 4 times 4, we got 1 point. 4 times 4, we got another point. 4 row, 4 column, 1 point. 4 row, 4 column, 1 point. So eventually 4 by 1. Okay? So how to denote the symbol? We have a tensor, 4 tensor of the second rank, dot of 4 vector. So in notation, T mu nu A nu. After sum over mu, it should be a tensor, a vector. How to prove a vector? A vector transform in Lorentz transformation. So prime system. So T prime mu nu A nu prime, A prime nu. And this one transform as this form. Okay? We learned this one before in the previous item. And A nu Lorentz transformation. Now we have prime prime, so become a delta. This one and this one here has become a connector delta. Okay, so later on it's become this one. This Lorentz transformation between mu and gamma. And what else? This one give us one notation. Delta alpha delta alpha delta. I'm sorry. We have we use delta a lot. However, this is Kronecker delta notation. This just means is a notation only. Okay, sum over delta give us this one, but it's not the same. But remember, we have these terms. This is a four vector. Four vector. All we need to do is they transform in the same way as Lorentz transformation. So this one uh, is transforms as a four vector. Okay, up mu gamma sum over gamma. We got mu. Okay, we prove it. It's transformed as a four vector. So this one transform. We can have different expressions. T mu nu a nu. We can use a metric tensor G mu sigma T mu sigma. Okay, we can change this one and G alpha mu. Okay, and then these two can be read into a connector delta sum over mu, sum over nu, so become sigma and alpha. Okay, sigma and alpha, so become sigma sigma T mu sigma A sigma. So in this way, we can express as, remember this is a row vector, but we express as a column vector. A row vector is difficult to operate. However, in terms of column vector, you can use a metric representation. So if we want to use a metric representation, sometimes you have to change form using a metric tensor to change the form. That will be much easier to understand. Otherwise, you will be confused. Okay. Item number 9. The four dimension or four divergence of a four tensor of the second rank. Okay. Once again, we have a tensor operation. We just tell you the inner product. Now we will tell you the four divergence of a four tensor of the second rank. It denoted as this one. And prime system T prime mu nu. After summation, we have mu. Or we can write into this form. That is control variant. That's covariant. Covariant as a homework, you should prove by yourself. So prove this one. This one. First, let's write it as a vector. It should be a four vector. A four vector should be transformed as the Lorentz transformation. So divergence, four divergence of a four tensor of the second rank, mu, write into this form. X prime mu, nu, T prime mu nu. Okay, and then we can write into this form, change to here, sum over x alpha. Okay, and this one you can use two, one for mu, the other for nu. Oh, sorry, mu nu, and then we have the same mu here, nu nu. Okay, just write it down, write it down. So eventually we got a connect delta again. This connect delta sigma alpha, so we can sigma alpha into an inner product. So it becomes a four divergence of a four tensor of the second rank, and the component is gamma. Okay, and this one is Lorentz transformation. So it transforms just like Lorentz transformation. Okay, you can prove by yourself. You can prove by yourself. Just cover your textbook like this and try to derive all the equation by yourself. T mu nu prime x mu s nu. Practice makes excellent. You need to practice, practice, and practice. Okay, so eventually you got the same notation, a different notation. That's covariant, contravariant, that's covariant, covariant. Okay, contravariant. So we got two expression. I use a blank regions is to give you a chance to write it down by yourself. Don't try to copy. You can actually, how to prove this one is quite similar to this one, but you got to practice by yourself. Otherwise, you don't know how to prove this one. If I give you a chance to prove these 11 items without open book, closed book, closed book, can you derive? Maybe sometimes I will give you a test as quiz number 2, for example. Okay, one more time. This one is can be read into this form: mu nu nu. Okay, partial nu partial mu nu. But remember, this is a column vector. This is a 2 by 2 matrix. It's not matched. It's not a row vector. So therefore, we should change the notation. The format in the metric representation is inconsistent. How to solve it? We can rewrite the format, this one, into this form, and partial once again, and we can change it into this form. So 1 by 4 times operate on 4 by 4 give us 1 by 4. Okay, so you can derive the correct form for this one with the same approach. Okay, actually it's much easier. That eventually we got a four vectors, four vectors. This is with the same approach. It's an extra point. send your answer to me. You got 1 point. Or upload the file to uh, extra bonus. Just upload the file to the extra bonus. You got 1 point. If your calculation, your derivation is correct, you got 1 point. Okay. Item 10. We still have last two items. 1. Item 10. A 4 tensor of the third rank. 4 tensor of the first rank is a 4 vector, just 4 components, 4 quantities. 4 tensor of the second rank is a 4 by 4, so it's a 16 quantities. So obviously 4 tensor of the third rank is a set of 64 quantities. For example, if we have a G, lambda, mu, nu, then transform will need 3 Lorentz transformation. Okay, 3, not just 1, not just 2, 3. If F mu nu is a 4 tensor of the second rank, then we can write into this one is a 4 tensor of the second rank. That's the first problem. The first problem. So F prime system can be used this one, 2 Lorentz transformation. F prime, we have 2 Lorentz transformation. The first one for J component. Second for K. Okay, so if we use this one, write it down again. X prime partial F prime mu nu. Okay, so X prime lambda. Then you need to write it down, partial this one, and this one can be write into Lorentz transformation for a 4 vector. Okay, now you can move this one to here. So eventually we got 3 Lorentz transformation, 1, 2, 3, and partial I F J K. If you don't want to write this form, you just express as this one. That's a superscript, which means there is here subscript, and you have 1 Lorentz transformation, lambda I for here, another Lorentz transformation, J, another Lorentz transformation, K. It's transformed as a 4 tensor of the third rank. So therefore, this is a 4 tensor of a third rank. Okay, we prove it. More information. Problem 2. Show that this one and permute. After the permutation, we got change. Eventually, we got a 0. That's invariant in form. Doesn't change. That means doesn't change under Lorentz transformation. So if this one is 0, then prime will be 0. That's invariant in form under Lorentz transformation. Okay, how to do that? We just write it down again. This one, we need 3 Lorentz transformation. Use the property we learned before. 3 Lorentz transformation. But this time, 3 Lorentz transformation. 1, 2, 3. Transform from prime to unprime. From prime unprime to prime, okay? Use the same property. So what's next? Next one, we will sum over these three, permute, prime, 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 prime. And we will have the same notation here. But here is different. But remember, this one is 0. So after Lorentz transformation, this one will be also 0. 0 times this one is 0. Okay? Therefore, before 0, transform to prime system, still 0. It's invariant in form under Lorentz transformations. Okay, so we prove this idea. You should derive by yourself. That's why I block these regions. You should derive by yourself. Write it down step by step. Practice by yourself. Not of course, not by me, by yourself. Okay, last one. If a physical law can be expressed as a relation between four tensors of the same rank, a physical law that the same rank, a physical law can be expressed as a relation between four tensors of the same rank. That is, the right hand side is a four tensor of some rank. Right hand side is a four tensor of the some rank. Then its form is invariant in form in all Lorentz frame. That is, if we have just give you two examples. Example one, if a physical law is in frame K is in this form, A equals B and prime. Then prime system, we have A prime. We just write into Lorentz transformation. And this one equals B, B, B. So after that, this one becomes prime, prime, prime. Therefore, that means before I'm prime, in a new inertial frame, we still equals. That's equations. Equation do not change. A physical law do not change. It's always invariant in form. Okay, so that's good news. A physical law, that's the principle of relativity. If the physical law in frame K is four tensor of the second rank, we just use the notation here. So T, that's unprime. How about prime system? Prime system. Okay, prime system, we need two Lorentz transformation. But remember, Tij equals Fij because they are equivalent components. So equivalent components. So after Lorentz transformation give us F prime mu nu. That is first rank, second rank. It's invariant in form. Okay, so finally, in the following section, we examine the relativity mechanics in four vector formalism. In section 3, we will demonstrate laws of electromagnetism are invariant under Lorentz transformation. That's very critical. So one is relativistic mechanics, 力学. The other is a law of electromagnetism, including Maxwell equations and conservation of charge. They are invariant in form. We will express them as relations between tensors of the same rank. And from the Lorentz transformation of these tensors, we also obtain the transformation equation for various electromagnetic quantities. Okay, so next time we will talk about the second part, relativistic mechanics. And of course, we will show you some quantity is invariant and some conserved quantity, some are invariant quantities. Okay, that's dismissed. See you next time.